Hi, this is Gigi. I am going to go over the derivatives of basic functions and then a bunch of series of basic functions and then basic differentiation rules. Okay, so first one first, derivative of a constant. If you think about a constant, the graph of a constant, for example, y equals, say, 5, right? So that would be a horizontal line. And a horizontal line has a slope of 0, right? So we know from that logic, and the derivative is the slope of the tangent line. So given that logic, we would be able to say that the derivative of a constant is 0. But let's just use the definition. So, and notation is this, d of the constant over dx. We don't really read it like that. We read it as the derivative of the constant k with respect to x, right? That's what d dx is, the derivative with respect to x of the constant k. So based on the definition, you would say the definition said is f of x plus h minus f of x divided by h when h is going to 0, right? So that would be the derivative of, not 0, but the derivative function f prime of x would be the limit as h go to 0. And since the function is a constant, you will just have k minus k over h, which is 0 divided by h, which is 0. So the limit as h go to 0, 0 is 0. So we have just proven that the derivative of a constant is 0. Okay, now what about the derivative of a constant multiplied by a function? So here you have a constant multiplied by a function. Okay, so in this proof, let's assume that you have a function, a big function. B of x is k multiplied by some f of x. Okay, so then by definition, you would say the derivative of that big function is b of x plus h minus b of x all divided by h, right? Now, that is going to equal to limit as h goes to 0. And whenever I see x right here, I would plug in x plus h. So that would be k times f of x plus h minus k of f of x divided by h. That's the definition of derivative, right? So you would say that the derivative of the constant k multiplied by some function f of x with respect to x is going to equal to limit as h goes to 0. And we can see that each one of these have a k in it. So I can factor out a k. And then inside here, I would say f of x plus h minus f of x all divided by h, right? Now that constant multiple right there, when h is going to 0, where does the constant k go? Well, what's the limit of k as h go to 0? Well, does it matter that h is going to 0? No, k is going to stay k, right? And then this right here, the limit as h go to 0 of this portion, as we recognize by the definition, is the derivative of x. So we have just proven that the derivative of a constant multiplied by the function is the constant multiplied by its derivative. Okay, that's the second rule that we have. Okay, so if we know, for let's say g of x, for example, g of x is 5 multiplied by f of x. Okay, now if I tell you, given that f prime of 2 is, say, 3, okay, then g prime of 2 is going to equal to 5 multiplied by f prime of 2. And that's what this rule said. Okay, and so that would be 5 times 3, and that is 15. So that is an example of how this rule could be applied so far. Okay, so the derivative first, we know so far the derivative of a constant is 0. The derivative of a constant multiplied by a function is the constant times the derivative of the function. Okay, now our job coming next is to be able to find the derivative of all of the basic functions that we have, like how you had in algebra, know all the parent graph, right? If you know the derivative of all the basic functions and you can apply the rules, then you can take the derivative of more complicated functions. So that is where we are heading. Okay, so for this right here, what is the derivative of x to the n power? That's the power function. Okay, so according to this rule, it said it would be n times x to the n minus 1. Now what I want to do is to go ahead and prove that to you, that is the case. Okay, now in order to prove that to you, we should know what we call the Pascal, the binomial theorem, or you have probably seen this in a Pascal triangle. Okay, so but it looks something like this. When you expand out a binomial, it should look something like this, right? A plus b to the fifth would have a plus a to the fifth. The endpoint would be b to the fifth, and then there's stuff in between that has a and b in it. Okay, so we're going to use that here. Really, the binomial theorem is a general form right there. Okay, now the derivative of x to the n power. Okay, by definition, you would have x plus h to the n minus x to the n all divided by h. That's the definition of derivative, right? So now think about having to expand x plus h to the n power. What are we going to have? So we would say the derivative of x to the n with respect to x is going to equal to limit as h go to 0. Now, what are we going to see here? We are going to see first x to the n plus, okay, some constant, some number, whatever that might be. And in this case, it would be this right here, right? It would be n, x to the n minus 1 times h. There's your a, x is your a, and h is your b, plus a bunch of stuff in between, plus n x h to the n minus 1, plus lastly h to the n power, and then all of that minus x to the n. That would be this part right there, right? So x to the n minus x to the n is gone. And you can see now that everything here, all the terms here will have an h in it. Okay, where the power of h is increasing, right? So when you divide things by h, the only term that doesn't have an h left, this would be n minus 2. When you divide by n, this would be n minus 1, right? So really everything else here will have an h attached to it when you divide by h, except for this one right here. So that would be limit as h goes to 0 of x to the n minus 1. That's this term, first term right there without an h, plus everything else has an h in it. And everything has an h in it. When h go to 0, all of this will go to 0. That leaves us with just n x to the n minus 1. That's the derivative of x to the n power as x with respect to x, right? The derivative of x to the n power with respect to x is n x to the n minus 1. What does that mean? An example of that is let f of x be x to the 7 power. Well, what's the derivative of x to the 7 power? N is 7, so that would be 7x to the 6. So using this rule, you really don't have to use the definition of the derivative any longer. That's why we generalize that, right? That's why we have the power function rule for derivative. You bring the power down and take one less. Okay? Now, if we were to put things together, another example here. So in the previous problem, we can see that the derivative of a constant times a function is a constant times the derivative of the function, right? So an example of how that applies is, let's say g of x is equal to 5x to the 7th. What is the derivative of g? Well, that would be 5 multiplied by the derivative of x to the 7th. That's what this constant multiple rule say, which would be 5 times 7x to the 6, and that would be 35x to the 6. So in short, when we have polynomials, really, when we have things like this, we take the exponent, put it down, multiply by the constant, that gives us 35, and then one less is x to the 6. Okay? One good example of that would be, suppose the derivative of f of x is equal to, say, 5x to the 6th plus 3x to the 4th minus 2x to the 3rd plus 8x minus 2. Okay, now imagine having to use the definition of derivative for that. Okay, at this point, since we just proved the power function rule, and we also have shown the constant multiple rule, we can just go ahead and apply those rules to say, hey, the derivative of f of x here as the polynomial is, bring the exponent down. So multiply by 5, that would be 30x to the 5th, plus 3 is a constant. The derivative of x to the 4th is 4x to the 3rd, multiplied by 3 there, so that would be 12x to the 3rd, minus 2 times 6, right? Bring that down, that's 6. X, one less, would be square, and then plus this is exponent 1. Bring that down, 8x to the 0 power. But what do we know about x to the 0 power? X to the 0 power really is just 1. So we don't need to write that x to the 0 power. That will just be 8. And then the derivative of a constant is 0. So now, given the rules that we have so far, we can take the derivative of a polynomial. Wait a minute. Can we do that when it's plus or minus here without those connections? That would be true if we could, right? If we could add all the derivatives or subtract all the derivatives. So that leads us to this rule right here, the sum and the difference rule. Okay, so the sum rule said that the derivative of a sum is the sum of the derivatives. So yeah, you can just take, when it's addition or subtraction, you can take the derivatives and then add them together or subtract them. For this one, it would be the derivative of f of f minus the derivative of g. Okay? Would you like to see the proof of these? And to keep this video short, I'm going to go ahead and prove the sum and the difference rule in a separate video. But for now, know that it works. So I just said that you can add and subtract the derivative as normal. Well, what about when you are multiplying? Does that work? Does the derivative of a product equal to the product of the derivative? That's the question. Let's see. Okay, so let's do a little investigation here. If f of x is x to the 5th, then we know the derivative is 5x to the 4th. If g of x is x squared, then the derivative of g is 2x to the 1st, which I don't need to write the 1, right? Now, if I multiply the two derivatives together, it would be 10x to the 3rd, correct? Okay, now what am I trying to answer? I'm trying to see if the derivative of product is the product of the derivatives. Now, let's multiply f and g together first, and then take the derivative. I mean, if this rule was to work, then these two should be the same, right? So I'm going to multiply f and g together. X to the 5th times x to the 2nd, that is x to the 7. Well, what is the derivative of x to the 7? 7x to the 6. So what can you say about the derivative of a product and the product of the derivative? Not the same. Not the same. Okay? So remember that. The product rule is going to work differently. Now, if the product rule doesn't work, of course, the quotient rule is going to be weird. Okay? So in separate videos, I will prove these product quotient rules for you.